All right, well, good afternoon. Welcome to another fun-filled day of statistics. So my plan today is to start our second to last chapter. Believe it or not, we're almost there. We've got 2 more chapters to do, and we're going to start heading into the second to last chapter, the penultimate chapter, about linear regression. So we'll kind of spend a little bit of time reviewing the idea behind linear functions, because it may have been a while since you've actually seen them and played with them. And then after that, we'll get into the idea of regression, all right, and what we use it for. So that's my plan. But as always, I'm going to give you the first little bit of time here. Are there any questions about homeworks or anything else that are still out there? All right, so Bruno just said, can we look over questions 1 and 3 for goodness of fit? All right, I'll put those on the list. Hopefully you guys remember that I did extend the homeworks. So the chapter 11 stuff is actually due tonight at midnight. So you got a little bit of extra time if you didn't quite get to it. And I also shifted the project due date to next Tuesday. So, all right, any other ones other than those from Bruno? All right. Well, then let me go ahead and share my screen and we'll take a look at those. All right, goodness of fit. All right, so here's question number 1. So we've got 712 students from UC Berkeley are surveyed about whether they are from Northern California, Southern California, Central California, or from another state or country. Researchers interested in seeing if the proportion of students from each of the 4 regions are all the same. All right, so the table below shows the outcome of the survey. Fill in the expected frequencies. Okay, so this one, we're actually not doing the calculation of, or the test on goodness of fit. We're not actually going to go through that far. All we're doing is we're finding what the expected frequencies would be. Because remember, when we do goodness of fit, we're comparing our observed numbers, our sample numbers, to what we expect to happen, right? So we had O's and E's for observed and expected. So we're actually calculating the expected. All right, so the question is, how are we gonna figure out how many students we should expect from each of these regions? So how do you guys think we're gonna get the numbers that go into expected frequency? Any ideas or thoughts?
Do you add up all the numbers and then divide by the thing, or?
Okay, so when you say add up all the numbers, do you mean the observed values?
Yes.
Okay.
And then divide it and use that as a sum, and then we take the frequency and divide it by the sum.
Okay. So we're actually not going to take the frequency and divide it by the sum. That would tell you what percentage of the students that were sampled come from those different places, right? Because if you add them all up, that gets you the total number sampled. So if you were to do that, say like for that Northern California, take the 158 and divide by the total, that's going to be what percentage of students came in the sample came from Northern California. So we don't want to quite do that because that's not going to be expected frequency. That's going to be our observed percentages. But that's a good idea of something to do with these. It's just, it's not going to get us what we want for these boxes. And I'll give you a hint. It's somewhere in the wording. Something in the wording here tells us what we need to do to get these expected frequency numbers.
We divide them equally, so we divide them in 4 portions.
There it is, exactly, because it says here, right, researchers interested to see if the proportion of students from each of the 4 regions are all the same. So the researcher thinks, right, is checking, they're thinking that it should be uniform, right? If the distribution is all the same, that's uniform distribution, which means it should be divided equally. So every one of these boxes should hold the same number. So what we need to do is figure out the basically 1/4 of all the respondents. So we could go ahead and just add up these 4 numbers, or use the fact that they told us that there were 712 students. So what we can do is take that 712 and divide it by 4. And I think that's 173. All right, so if we truly think that it's uniform, then every one of these should be 173. All right, so just because we expect it to be the same, or we're looking for it to be uniform, we can just divide them all and they're all equal. So let's see if we get the green check mark. What? Oh, yeah, how about 178? That's what I get for trying to divide this in my head. Let's try that again. There we go. Okay, sorry about that real quick arithmetic error. But anyway, if it were uniformly distributed, there should be 178 from each of the 4 regions based on 712 students being interviewed. Okay, so like I said, this one we're not actually doing the goodness of fit. We're just finding what the expected frequencies should be. All right, so let's go take a look at number 3. Hopefully number 3 is making us do it. Yep, all right, cool. Okay, so this one, are phone calls equally likely to occur any day of the week? The day of the week for each of 455 randomly selected phone calls was observed. The results are displayed in the table below using alpha equals 0.01 significance level. All right, so part A is going to be just like what we did. We need to put in what we expect as our frequencies. Again, just like with that other one, if we go back and we look, it says phone calls equally likely to occur any day of the week. That means we're thinking that it should be uniform, that we're going to get the same number of phone calls regardless of the day. All right, so this time we're going to take our total, and instead of dividing by 4, we're going to divide by 7, because there are 7 different days. So we come back up here, there were 455 respondents, or phone calls that we looked at. If you divide that by 7, you get 65. So every one of these boxes should be 65, because that's what we expect if it is uniformly distributed. Okay, so the correct statistical test to use we're going to do a chi-square goodness of fit. And again, yes, I know that this section is called goodness of fit, and so we know we need to use it there. But in general, you need goodness of fit when you're trying to see if the results that you got from your sample follow a distribution that you're already expecting, right? So we're looking at comparing this against uniform distribution. So we're going to see how good does it fit uniform distribution. All right. So of these 4 choices for the null hypothesis, which one are we going to pick? In goodness of fit, it's always the same null hypothesis. So which one? 1 through 4. Go ahead and just throw in your chat box and 1, 2, 3, 4 in order from top to bottom. Which one do you think is the null hypothesis? All right, so seeing lots of 4s. And I definitely like that. We are going to use the 4th option, because what it always is in the goodness of fit is that that we do match our expected distribution. Okay, that the sample size actually shows that our distribution is what we think it is. Okay, so in this case, it's that we think that it's uniform. So the distribution of phone calls is uniform. All right, so then the alternative hypothesis is going to be just the opposite of that, which is distribution of phone calls is not uniform. All right, so degrees of freedom. This is where we start having to think a little bit, because in all of the times that we used the chi-square distribution, we calculated degree of freedom a little bit differently. But what is it for goodness of fit? Do you remember? It's actually a very easy calculation. All right, thanks, Bruno. He just put in their categories -1. So it should be 6. All right. And Allie, you just put their columns -1. It really should be rows, because rows go across columns. It could be columns. Yeah, no, that's all good. We could have represented it as columns, right? If we had made it so that the chart was turned sideways, so it was like Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday. So we could have done that. But yeah, so this one, it would be number of rows -1, which is 6. All right, so now let's go do our calculations. So we need the test statistics. That's going to be our chi-squared. And then the p-value. And then once we have that p-value, we'll compare it to the alpha they gave us and then make our decision. So let me go ahead and switch to the TI-84. And we are going to go to list first, or let's go stat, let's edit. Let's get this information in. So you may remember that what we're going to do if we're going to use the calculator is we're going to put our expected values in one column and our observed values in another. So I'm going to go ahead and put in those numbers that we had found, or that we were told, and we'll go ahead and put those in my column L2. So we had 63, 60, 87, 42, 70, 62, and 71. All right, so there were the 7 values that we actually found. So when we looked at those phone calls, these were actually the numbers from Sunday through Saturday. So I'll go ahead and arrow over. We'll go here into this second list, and I'm going to put what we expect to see. If it's uniform, then these are all 65. So basically, I'm just duplicating that chart that we filled in on the computer. All right, so there's our L2 and our L3. So now let's go do the chi-square distribution. Use that. So we're going to go over to stat, come back to tests, and we're going to use the chi-square goodness of fit test. All right, so it asks for the column with the observed and the column with the expected, and those were L2 and L3. So we don't have to change those, but I do need to change my degree of freedom. In this case, it's 6. All right, so we let it do its thing, and it's going to spit out a chi-square and a p-value. So let me just write this down. So I don't know if you guys have gotten to this point yet, but whenever I do any of these tests, the very first thing I key in on is the p-value. I don't actually look, I mean, I will look at the other things, but the first number that I'm drawn to is the p-value, because that really tells me all kinds of stuff, right? So anyway, there's our chi-square and there's our p. So let's go back to the homework question. So we can put all this stuff in. All right, so the test statistic, that was our chi-square. So it was 17 point, how many decimals? 108. We round to the 3rd decimal place. And then the p-value to the 4th decimal place was 0.0089. All right, so that's just what our calculator, the black box, tells us. So now let's see how p relates to alpha. Alpha was the 1%. We come back here, alpha was 0.01, so 1% significance level. And our number is smaller than alpha. All right, so what does that tell us to do? When we're smaller than, when p is smaller than alpha, what's the result always? Do we accept it, fail to reject, or reject?
Reject.
We reject. All right, so at a 1% significance level, at alpha equals 0.01 level, we're going to go ahead and reject this null hypothesis. Okay, so the null hypothesis, remember, was that the distribution of phone calls is uniform over the days of the week. So we're going to go, nope, it doesn't look like it. We actually have statistical evidence to suggest that that is not true. So if the statement is that it's uniform and that's false, then that means that it appears that it is not uniform. So we're going to come in here and we're going to see, I think it's this 3rd one. There is sufficient evidence to conclude that the distribution of phone calls is not uniform over the days of the week. All right, so we're going to go ahead and reject that null hypothesis. All right, well, hey, look at that. We got our 3 points out of 3 points. All right, so does that make a little bit more sense? I'm going to guess, Bruno, that this had this sort of the similar issue with question number 1, is trying to figure out how to get these numbers that we were comparing against.
Yeah, it makes a lot more sense now.
Okay. And sometimes they're given to you, right? Sometimes those numbers are actually given to you as what were expected, but sometimes we have to calculate them. Remember, the other big way that we do that sometimes, is multiplying by the percentage. That's a pretty common thing too, where you'll be told, oh, okay, studies have shown that 15% of phone calls are made on Sunday, 10% are made on Monday, yada, yada, yada. And then you multiply those by your sample size to get what you should expect to find. All right. And your expected can be a decimal. It's totally fine. Just be careful when you're using the computer to answer it how they want, right? Because sometimes they'll say, round it to the nearest whole number or something like that. But in terms for a mathematician, statistician, it's totally fine for expected value to be a decimal, even on something like this where we are counting. So. All right, so sounds like we're okay there. Any other homework questions before we jump into new stuff for the day? No? All right, well, then I'm going to go ahead and switch up to the whiteboard, and I'll be right back with you. All right, so today we're going to talk about linear regression and what it does, what it means, how we use it. So that's kind of what this chapter is all about. But before we get into linear regression, I want to remind you about linear functions. So this is from algebra. It may have been a while since you've seen these, so I want to make sure that we're all kind of on board with them. Because if you're not really comfortable with the idea of lines, linear functions in general, we're going to be kind of sunk when we try to move forward. Okay, so this is going to be review. It should be review for most of you. But of course, if you have questions, please don't hesitate to ask. All right, so let's just start with linear functions. All right, so functions, hopefully you remember at least a little bit about functions. Functions are the old, you plug in a number, you get out another number. And linear functions, these are ones whose functions whose graphs are lines. So not curves, but lines, right? A lot of people will call these straight lines. I don't like that term because a straight line, to me, that's redundant information. A line is straight by definition. But these are the graphs. These are ones that have graphs that are lines. Okay, so the equation for one of these things is y equals a plus bx. Now, you're probably used to seeing this written differently. Because if I were to ask you the equation of a line, probably the first thing that comes to mind, and I'm going to write this in a different color down here, would be y equals mx plus b. All right, so you probably remember that. All right, now we're going to look at it a little bit differently. We're going to look at it as y equals a plus bx, because that's what that's how statistics tends to write it. That's what you're going to see when you use your technology. So we're going to look at it like this. Now, I'm not a huge fan of that because these B's are different B's. I really don't like that, especially since we drill into you guys when you learn algebra, y equals mx plus b. I don't like switching it on you, but that's not for me to decide. I wasn't the one who invented these statistical programs. I just have to deal. All right, well, this is really the same thing. It's just written in a different way with some different letters. Okay, but this is the equation of a line. It's y equals ax plus b. All right, so some things about this. These two letters, A and B, represent different things with our line. Okay, the A, this is what we call the Y-intercept. And the B is the slope. So all linear functions have a Y-intercept, and they also all have a slope. So what those are, again, this is a bit of a blast from the past probably. If here are our axes, the x's and y's here, right, where x is left and right and y is up and down, and then we were to graph just some generic line. So we've got this line right here. Let's start with the y-intercept. The y-intercept is where our graph crosses the y-axis. So that's this point right here. And that point has coordinates 0, comma, a. So if we're given an equation like this, whatever the a is, that's the place where we cross the axis. All right, so there's your y-intercept. Now, the slope, this is a little bit more complicated just to show on a picture, but the slope, what it tells us is it's basically the direction of the line. It tells us what direction the line is pointing. So you might even hear me use these words, but these are words I tend to say when I'm teaching this, especially early on. I think of the y-intercept as the anchor of the line. It makes the line stay put. Okay, so that tells us where we're going, like or where we're going to be. And then the slope tells us where to go from there, what direction to head out. Because if I wanted to do a line, I mean, if all I knew was that the line went through this point, I have all kinds of different choices, right? Like think about my pen as a line. I can rotate it in all kinds of different ways to get different lines that go through that point. Well, each one of those has a different slope because the slope tells us what direction to go. All right, so it's the direction of the line. Another phrase that people use for this is steepness. It's how steep that line is. Right, so imagine like you're hiking in the mountains. Right, so you're going to go take a hike up to the top of Mount Talac. There are going to be places that are flatter, places that are steeper. Well, slope is also a measure of that steepness. So you can think of it in a couple different ways, but basically that's what the slope is telling you. All right, now in terms of calculating that slope, the slope, there's a little mnemonic device for this. It's the rise over the run. So we say rise over run. So rise is how far we're going up and down, and run is how far we're going over. So in formulas, or well, so this would be the change in y divided by the change in x. You might have also seen a formula for that once upon a time that has little triangles in it. Those triangles are the Greek letter delta, and that's the letter that mathematicians have decided to use to show change. All right, so if you ever see that, that just means it's a change in that quantity. So basically, if we had 2 points on this graph, any 2 points that happen to be on this line, the run is how far we have to move over left and right to get below that next point. And then the rise is how far we go up or down. So you probably remember having to calculate slopes from points. You just take the difference in the y coordinates and divide by the difference in the x coordinates. All right, so that's how a slope is defined, and that's how we calculate it. But really what's going to be important to us, especially in statistics, is the value of the slope and what that means. All right, so first things first, if your slope is positive, all right, so this b value is a positive number, this means that the line goes up to the right. And so this line that I drew here has a positive slope. As we go to the right, this line is going upward. If our slope is negative, that means that the line is going to go down as we go to the right. So think about what that would look like. If we go to the right, we have to go down. It means we're going to be tilted this direction. So positive slope, negative slope. All right, so generically, here's a line with positive slope, and there's a line with negative slope. The bigger the slope is, the further it gets from zero, the steeper the line. All right, so we'll go ahead and put that over here as well. Something to remember about it. So just let's see. The further the slope is from zero, the steeper the line. All right, so if we have a slope of say 10 versus a slope of 5, the slope of 10 is going to be a steeper positive line than the slope of 5. Which then leads us to, if the slope is 0, what that means is that this is actually a horizontal line. And I know sometimes we forget horizontal, vertical, and what all those different things mean. So another good way to think about this is a quote unquote flat line. All right, so if your line is flat, horizontal, it has 0 slope. All right, but if you think about slope again as rise over run, that should make sense. If we have a slope of 0, that means there is no rise. There's no fall. We don't change our y value. We just stay where we are. So it's flat. Okay, so hopefully that's a good little review of what linear functions look like, and these two important things, the intercept and the slope. Because when we get into regression, when we do linear regression, a lot of what we're gonna have to do is interpret, like we're gonna get equations of lines, and we're gonna have to interpret what those things mean. What does the y-intercept in the case of whatever study we're doing? What does the slope mean? Right. So it's going to be really important that we actually know those. There's one more thing I want to mention about linear equations and linear functions. And this is the fact that we have two variables, right? We've got y and we have x, but those two variables, they don't play the same role. They do different things, right? And so in the situation where we've got y equals ax plus b, sorry, a plus bx. All right, this guy y, we call this one the dependent variable. And x is the independent variable. All right, Bruno, take care. All right, so x is an independent variable, y is a dependent variable. So they're both variables, but we say one is independent, the other is dependent. This is not at all when we talked about two events being dependent or independent when we did probabilities. This is a completely different usage of these words. Okay, so just be aware of that. We say x is the independent variable because that's the one that basically we can just choose and we can just plug in. And we say that y is the dependent variable because its value is determined by the x that we plug in. Right, so remember with functions, you choose a number to plug in, you get something else out. That one that you're just choosing to plug in, that's independent. You're just deciding to plug something in. But once that's chosen, your other variable is determined. Okay, so that's why we call it an independent and a dependent variable. So when you see those terms, be very aware that they mean something different than with probability. So there are linear functions. So what we're going to start talking about is what we call linear regression. All right, so you see that word linear, that should immediately make you think lines. So when we do linear regression, we're doing something with lines. Now, what that something is we're going to find the equation of a line that best fits a given set of data. So we're going to be given some data, and we're going to try to find a line that fits it as best as possible. And we'll talk about what it means for it to fit best. Because mathematicians, we have a way of defining what we say is best. but we're going to find an equation, a line that best fits the given set of data. Now, the data that we're given has to be what's called bivariate. And bivariate, if you just look at what the words are, so bi, that prefix means two, right? Like bicycle, biplane, biped, 2 legs, 2 feet, right? So bi means two, variables. All right, so bivariate data, this just means that it has two variables. Now we haven't really dealt with things that are bivariate much, right? Like just go back to think about those goodness of fit ones that we were just working on from the homework, right? The goodness of fit, there was only the one variable, number of phone calls per day. Number of students from insert geographic region, right? So that was only one, like we only have one variable. Now we're going to have paired variables. We're going to have paired data. All right, that's another way to think about this. Bivariate data means that it's paired in some way. All right, so I'm going to go ahead and put that here as well. But I want you to realize that the paired data, it doesn't necessarily have to be like what we saw before with paired data. Like remember when we did something like here was the person's cholesterol before the drug and then after the drug, right? So it was two things that were related to the same person, same quantities. This could be a little bit different. This could be, age versus blood pressure. It could be years of college versus amount of money earned, right? They can be completely unrelated things, or well, not unrelated, but they don't have to be the same quantities. You just have to be comparing two things together. All right, so let me actually just start off with an example. Let me give you some data so you can see what the this bivariate data looks like, and then we'll use this as an example of how we go about finding the best fit. So, for example, let's do this. Let's say that we're looking at a study of blood pressure versus age. All right, so we're going to study systolic blood pressure in men of different ages. And maybe we want to see, all right, does it look like age is a factor in blood pressure? Is age actually a factor in the blood pressure that somebody has? All right. So we go and we take some data, and we're going to have in it some subjects. We're going to record their age, and then we're going to record their systolic blood pressure. So if you are curious, because you're probably like, systolic, what does that even mean? So I don't know if you've ever had your blood pressure taken, but there are always two numbers. And those pressures, they have to deal with what's going on as the blood is getting pushed through, right? There's pressure on your walls. And so there's systolic and diastolic. This is always the first one, the bigger of the numbers. Right? So that's the pressure that's being felt as the blood is actively being pumped through. All right, so we do this study and we get this information. All right, so we've got 7 different ages that we look at. So we have 16, 25, 39, 45, 49, 64, and 70. Okay, so we have 7 patients, and we take their blood pressures, and we find these values. All right, so there are the blood pressures for those 7. So first question, just looking at those numbers, does it appear to you that there's a relationship between age and blood pressure? Just what do you think? So Willie says yes. Okay, so we're getting a bunch of yeses, and then Allie even put in there, it looks like that it rises as they get older. And I think that definitely appears to be the case, right? I mean, you look at these youngsters, youngsters, like the age of a lot of you guys, right? But think about the 16 and 25-year-old, that their numbers 109, 122 compared to these old farts. And I can say that because I'm actually more in here. But the older ones, I mean, the 180s versus the 100, 122, I mean, it definitely looks like it's getting bigger as we go. So it definitely looks like there's some sort of relationship. So maybe we want to see, well, is it linear? A linear relationship? But this is what regression is all about, is trying to look at data like this that's bivariate. There are 2 variables here, right? 2 things that are changing. One is the age of the person, and the other is their blood pressure. All right, so how are we going to go about doing it? Well, the first thing we're going to want to do, or the first thing that's useful when we're dealing with data like this, is to draw a picture of it. And so what we're going to do is we're going to create what's called a scatter plot. All right, so what is a scatter plot? Well, this is going to be a graph that has a point for each pair of data. So you remember your points are x comma y. So what we're going to do is we're going to pick one of the variables to be x and the other one to be y. Again, with the idea that we want x to be the independent variable and y to be the dependent variable. Now, in a situation like this where we have some data, deciding x and y, it really depends on what we're trying to determine. Now, in the case of this study, what we're looking at is there a relationship between age and blood pressure? Like, knowing your age, is there going to be some sort of blood pressure we should expect or think should be going on? So in this case, age is going to be our independent variable. And blood pressure is dependent, because we're trying to see what is your blood pressure given your age. Right. So what's the result of choosing an age? What's the result on the blood pressure? All right, so let me actually show you what this would look like using the calculator. So I'm going to go to the computer and I'm going to share the screen with the calculator. So I'm going to show you how to do a scatter plot. And in that process, we'll see what it looks like, right? But it's just going to be a collection of dots. All right, so let me pull up my calculator here. So we'll go ahead and share the screen. All right, so there's our calculator. Now, in order to do this, we need to get our data in first. So we're going to do what we always do when we've got data. So we're going to come over here. We're going to go to Stat, and we're going to Edit. All right, so I'm just going to go ahead and reuse L2 and L3 here because we don't need this information from the homework problem anymore. So let's put in the values. So I'm going to put the ages into the first one. It absolutely doesn't matter which one you put where. We just need to make sure that we know which is which. So the first one's going to be the ages. We'll go ahead and just get those in. All right, so they're the ages of our 7 subjects. And then we'll arrow over and into this column, we'll put their corresponding blood pressures. So 109, 122, and so on. While I'm doing this, I do want to point out that it's very important that when you enter these, you enter them in the same order. So that if you were to look across any one of these kind of rows, let me tell you what I mean. I'll point to it. So like you're to look like from here and over, that those things are matched together, right? So like the 70-year-old goes with the 180 in terms of their blood pressure, or the 45-year-old goes with the 165, and so on. All right, so it's super important that you've actually got those things paired up properly. All right, so we put in our date. Now we're going to go somewhere completely different. I want you to look right below the screen. You can see there are buttons that say Y equals, and then window, zoom, trace, and so on. And then above those, there are some other things, like it says stat plot, table set, format, and so on. Well, we're going to go to stat plot. So since it's in the blue, we got to do second, and then this button. All right, so again, stat plot. It was second, and then the first button there says Y1. These are all graphing things. All these buttons have to deal with graphing, and we haven't done any graphing really with the calculator up to this point, other than I think maybe we drew a couple of graphs of like distribution functions. All right, so you notice it's got a whole bunch of choices here. It says plot 1, plot 2, plot 3, plot, okay. So we can do more than one plot at a time, but we're going to go ahead and just do plot 1. So we're going to hit enter. If you wanted to go to a different plot, just arrow down and then you could hit enter. But we're going to go to plot 1 and hit enter. So you have all kinds of options for this. So the first row, you notice how it says on, off. It does exactly what you think it does. If we were to arrow over so that it was off and highlighted, this means that it's not going to draw the graph. So whatever this is set up as, it's not going to draw it. We do want to draw it, so I'm going to go ahead and put it back on, but that's just a on-off. Now, if you go down to the next list, you'll notice that there are all kinds of different things here, all kinds of different pictures, and those all represent different kinds of graphs. Some of them may look familiar. Like, look at the second one from the end. I'll highlight it right now. If that kind of looks familiar, it should. It's kind of like a box plot, box and whisker plot, right? So we could actually use it to draw a box and whisker. This would be a histogram or frequency. plot, but we want a scatter plot, and scatter plot is the very first one where you just see a whole bunch of little white dots. And that's what scatter plot does. It just draws dots of the data. So that's the one we want, so we'll go ahead and leave it. In terms of the lists, I think these are not how I want them. The X list, I want that to be my age, and I'm pretty sure that that was L2. So let me change that to L2. So we'll go second, L2. And then I want my Y list to be L3. All right. So we just told the calculator where our data is held. The next one down, notice it says mark. It gives you different options for what you're going to see when you draw your graph. So this one's going to give us little boxes. You can have plus signs. You can have little circle-y things. You can have dots. Like there are all kinds of different choices. We'll just go ahead and leave it as a box. And then again, you can choose a different color if you want, but we'll go ahead and just leave it. All right, so we've got our plot set up now. It's on. It's going to be a scatter plot. And we've got our X and Y list set. So I think we're good. So I'm just going to hit enter. All right, so now what we want to do is we want to draw the graph of it. All right, before we do that, we need to do one more thing. Again, if you look at the buttons that are up near the top, on the middle one, oh, sorry, not the middle one, the second one, it says window. We're actually going to press that because this is where we're going to set the X and Y values that we want to see in our graph. And you want to use your data to help you do this. So think about our X's. Those were ages between the ages of 16 and 70. So what I'm going to do is I'm going to look at an X min of 0. So my smallest X is going to be 0. And my biggest X, I'm going to make it 100. Because all of my ages are between 0 and 100. Now, the 0 and 100, was there any specific reason for that? No. I'm just using 0 and 100 because it covers everything. And in fact, we can adjust this later if we need to. Okay, so then if you look at the next one down, so X min, X max should make sense, right? They're biggest and smallest X's. But now this guy says X scale. This is just going to make marks on our X coordinate or our X axis so we can kind of keep track of where we are. So, whew, excuse me. I'm going to do this in 20s. Oh, no. My calculator froze. All right. Hold on here just 1 second, guys. Let me stop share for a second. I'm actually going to pause the recording. We'll be right back. All right, so I think we got that fixed. So let's go back and try this again. So you're setting our window. Again, it looked like for our X's going from 0 to 100. Oh man, maybe I spoke too soon. Oh, there we go. Okay, so go from 0 to 100. And then in terms of our scale, we're going to go every 20. So we're just going to have a little mark on the screen, on the axis, every 20, just to help us see where we are. Okay, so now we need to go to the Y's, and the Y's were the blood pressures. I'm going to go from 0 to 200. Since the highest blood pressure we saw was 183. It's going to be good there. And how about this time for our scales, just to change it a little bit? How about we go 50. Now those other things that are down below, XRes, delta X, trace step, don't worry about that. We're just going to leave those alone because they're not going to affect anything here. All right, so we have this all set up. So we change our window. So now we're going to graph. And to draw the graph, you're going to see that there's the button on the far right there underneath the screen. It says graph, so we'll click on that. Oh, you know what? I think we need to change our plot again. Hold on. Yep, this is still wrong. Okay. I think when we set our plot, it didn't get saved when I had to turn it off and back on again. So let me just go down here real quick. We have to change the list. It was L2 and L3. L2. And then we'll use the squares. Okay, I think that's good. And then the other thing I want to check is that our lists actually got stored, because I think maybe they didn't. Okay, let's do the stat edit. Yep, it still has the old information. Okay, so give me 1 second. I will put those blood pressures back in. All right, well, I apologize for this slight technical difficulty, but we should be good once I get these in. So there were our blood pressures, and then our ages. Okay. Now that we got everything, again, let's go and hit graph. Okay, so we'll hit the button that says graph. It's between the arrows on the screen. Okay, so there is the graph of these data points. So this is what we call a scatter plot. All right, it's just got the various values. And the way to read this, let me kind of show you on the bigger screen here. So this horizontal axis, that's our ages. And you may remember I set this up so that there were marks every, I think it was 20. That's 20, 40, 60, 80, 100. So think about the person who was 16. There's the 16-year-old. It's less than 20. The 25-year-old, right, between 25 and 40. And so on and so forth. So the 39-year-old was very close to 40. So that was that person. And then the y-axis, that holds the blood pressures. It was 0 to 200. And I think I made the marks 50. So this is 50, 100, 150, and then 200. But that's how we can actually kind of read this graph. And the reason that I like scatter plots is it really helps you see whether or not this looks linear. So does it look like it's linear? Does it appear that a line would fit that data pretty well? I mean, probably not exactly, right? But it definitely looks like there's a linear trend to this. I'll kind of move my arrow in the direction of a line. So the question then is, what is that best fit line? So my recommendation when you're given data, very first thing is draw a plot of it. and see, does it look like there's a linear relationship? Does it look linear? Because they don't always. Sometimes they look very much not linear. But if they do look linear, you can start thinking, oh, all right, well, maybe we're going to do linear regression. All right, so let's keep talking linear regression and how we find that best fit line. So I'm going to quit sharing. We'll come back to this in a little bit, but let me quit sharing for now. But let's talk more about that best fit line and what we're looking for. All right, so we draw the scatter plot, and it definitely looks like there's a linear pattern, right? And in fact, we would say that this one was a strong pattern because it looked very linear, right? And so sometimes what we'll talk about like a strong versus weak. And an example of the strong was like what we just saw, where our data points, I'll just make little X's for our data points, definitely look like there's a line going on, versus a weak would be, well, maybe it's something like that. Is there a line that best fits that? Is that linear? I guess kinda, maybe, sorta. Right, like this first one, it's pretty clear that there's going to be a best fit line that looks like this. All of the data is somewhere near it. This one, it also looks like there's probably some linear relationship, but it's not quite as strong. Those data points don't fit on the line as well. They're more spread out. All right. Now, strong versus weak is kind of a subjective thing, right? It's just a what's strong to you may not be strong to me. But mathematicians have a way of really quantifying this so that we know how good of a fit it is. But there's a strong relationship versus a weak relationship. You also have what we call deviations. Right? And the deviation, this is again a point that doesn't quite fit the rest. So it's not a standard deviation. But you could also have a strong relationship with a deviation. Like let's say this was our set of data, and then there was this one as well. So that one that I just drew is what we would call a deviation. It's kind of like an outlier. You may remember when we were talking about data and when we were doing like box and whisker plots, right? That we had outliers, things that didn't really fit the rest. Well, in the case of scatter plots in linear regression, we call that a deviation. All right, so it is possible to have a deviation. So you want to be careful and don't just rule something out and say, oh, there's not, it doesn't really look very strong because there's this one that's really far away. Just go, well, without that one, it looks pretty strong. I don't know that there's one data point here. I don't know, maybe this one would make it, if that went away, it look a little stronger. I don't know. But anyway, just be aware that we might have some deviation. Well, now that we know what we're looking for, how do we find it? Well, there is a way to determine what we call the best fit line. Okay, and that's what we're going to be looking for. Is what is the line that fits that data the best? And what does that even mean? Okay, well, this best fitting line, we actually have a name for it. It's called the least squares regression line. So that's its name. Okay, the least squares regression line. Its name, it falls from exactly what it is, you'll see. So it's a line that we're using for regression. Kind of, see what's going on with this data. And it comes from the least squares process. I'll talk about what that is. You'll see why I guess that in a second. All right, so let's take this example right here, the first one that was kind of strong. Let me erase the deviation because we're going to go with it. We got a pretty good set of data here. All right. But suppose that this is our set of data and this is our best fit line. So some terminology that we need before we, in order for us to continue here. First of all, we're going to talk about Y versus Y hat. So what I'm going to do is I'm going to look at a specific data point. Let's look at this third data point, the one that's a little bit below the axis. Okay, so we're going to look at this guy right here. I'm going to try to make it a little bit. All right, now the Y value that corresponds to that one point, we're going to call that Y naught. Okay, so remember with your graphs, when you draw graphs like this is your X, so we're going to call it X naught, and this is our Y. I'm going to call that Y naught, a little zero. We're going to call that a naught, Y naught. Now I'm interested in that compared to the point that's actually on the line. Maybe let's just call that X. Now this point, we're going to say that its Y value is Y hat. You remember that little caret symbol, the little kind of upside down V. So this is going to be Y hat. So Y hat, this is the value of the line. Given an X. And then Y naught, this is the value of the data. Okay, so we have two different Y values. The one is the data Y, and the other is what the line would suggest. So come back to this example with the blood pressures. We take the person who's 45. Their Y naught is 165. The Y hat, well, we'll figure that out. We'll see what the line actually gives us. Okay, so that's what that Y hat is. It's actually the value from the line. All right, now the next thing that's going to be important is the difference in those two values. So we're going to look at Y naught minus Y hat. All right, now that is this distance right here. We're going to use a curvy E to represent that number. Okay, so that's actually just the difference, like how far off from our actual data value is that line. And we call this the residual. So every point, every data point is going to have a residual. It's how far off from the line is our data point. Obviously, our line fits better if that residual is smaller. right? Like if this gets tinier, that means that our line gets closer to that point. And in fact, if the residual is always is 0, that means the line goes through the point. All right, so that's our residual. In terms of positive or negative, the residual is positive if the data point is above the line. If the data point is below the line, we're going to get a negative residual. So sometimes residuals are positive, sometimes they're negative. And the sign does tell you something. I mean, it tells you on which side of the line your point actually is appearing. Okay, but there's our residual. Now, like I said, we want small residuals. So the best fit line is going to be the one that kind of makes these things smallest. But here's the problem. Like we could make one of the residuals be small, but then it could make one of the other residuals get bigger. And so it might actually be a worse fit if we make one of them smaller. So we need to think about a total. What are we going to get if we have, a bunch of data points? Clearly, we're trying to do something with the total residual. But here's the problem. We can't just add the residuals together. Since some of them are positive and some of them are negative, we could actually add them up and get 0, which would be really good, right? If your total residual is 0, that would make you think, ooh, I went through every point. But that might not be the case because the positives counteract with the negatives. And so we might have every data point really far off. They just kind of cancel each other out, right? So we can't just add up the residual. So instead, what we do is we're going to add up the squares of the residuals. All right. So what we're going to do, we're actually going to look at the sum of the squares of the residual. So you guys remember your sum, the sigma notation, right? So we're going to do this. This is what we call the sum of squared errors. Right? Because we're adding up the square of those errors. And it's this that we're going to minimize. When you square, everything turns positive, right? All the values turn positive. So we don't have to worry about sometimes adding a negative to a positive and having those cancel out. So this is actually a better measure of fit. If we can make it so that the sum of the squared errors is smallest. All right, we'll go back to the name. Remember over here, the name of this thing? It was the least squares regression line. And this is where it gets its name. Least, smallest squares. We're going to add the squares and get the smallest sum. All right, so that's where it gets its name. The least square, least squares regression. Okay, so now we know what we need to do. We need to find those residuals. We need to square them. And then we need to minimize them. Now, for us, with our math background at this level, this is an impossible question. However, it's very possible if you know some calculus. And in fact, when I teach calculus, I show this to my students as an example of what we call optimization, finding maxes and mins. Okay, so this next bit, you're just going to have to trust me. This is one of those where you just smile and nod and go, okay, Bruce, whatever you say, sure. Okay. So if you do some calculus, so by the magic of calculus, here's how you find the equation of that line. Okay, so just again, smile and nod. So from calculus, our best fit line is going to be y equals ax plus b, where here's how you get a. So a, it's going to equal the mean of the y values minus b times the mean of the x values. So you know how to find the mean of the x's and the y's. Right? Add them all up, divide by their value. So that's what these two things are. And then the b, of course, is the other b. So we still need to know how to calculate b. All right, but again, real quick before I get there, let me just write that these are the means. Just in case you've forgotten. But that's what the bar over the top is, right? And those are sample means. That's the mean of the sample data. All right, so that's what A looks like. Not too bad. But of course, we do need to know B. So we got to calculate B. And here's what B looks like. It's a sum of x minus x bar times y minus y bar divided by the sum of the x minus x bars squared. Okay. So here's how you'd have to actually calculate this. Again, you need your averages for your means for the x's and the y's. So we calculate those. On the bottom of this fraction, what you do is you go to each of these data points, you take the average, and you see how far it is off of the actual data value. So let's just say the average for the ages was 40. I don't know what it is, but let's just say it's 40. So you would take 16 minus 40. How far is 16 from 40? Well, that's 24, and then square it. And then you do, okay, so 40, how far is that out from 25? Well, that's 15. Take 15, square it. 39 to 40, 1 squared. 45 to 45, 5 squared, right? And you take all those numbers and add them up. That's what goes in the bottom. On the top, you do the same thing where you look at how far are these from your mean, but you also look at how far the y's are from the mean. And you take those two numbers and multiply them together and then add them all up. All right, so this is when you go, yeah, thanks a lot, calculus students. Give us this horrible formula. All right, here's some good news for you. You don't need to know these formulas because your calculator already does. The calculator already knows how to do this. It will calculate these things for you, so you don't have to remember these formulas. Thank goodness. All right, but calculus brings us here. So you're not going to do this. I know you're not going to do this. Instead, you're going to use your calculator. So let me show you how you use the calculator to do that. All right. And there are a couple of ways that you can get it. So let me show you both of them. So I'm going to hop back down to the calculator real quick. All right. So here's our calculator with our beautiful plot of data. But this time, we're going to actually calculate the regression line. All right, so we're going to go to stat because everything we ever want is in stat, right? And the first way I'm going to show you this is to just calculate it. You run over to calc. And if you look down a little bit, you see here one where it says Lin Reg. Now, I'm going to warn you that so anyway, so we got here's our y equals ax plus b. Ignore my warning. Ignore my warning. Let's just hit enter. Let me show you what it's going to ask us. All right, so it says, what column holds your x's and what column holds your y's? All right, well, we've already got this set up, so it's list 2 and list 3. And then in terms of frequency list, we're not doing any kind of a frequency thing. We're not going to store the regression equation right now. We're just going to go ahead and calculate it. So we'll just arrow on down. We get calculate and hit enter. So it thinks for a second. And we get these numbers. All right, so I am going to write this down on the whiteboard. I'm going to erase those horrible formulas because we don't really want those anymore or need them anymore. But for this data, we've got y equals, and this I do need to warn you a little bit about. Notice that it says here y equals ax plus b, and I think when I showed it to you, it was a plus bx. Okay, most important is figure out what's slope and what's the intercept. The slope is what's being multiplied to the x. So in this case, it's the a. So we're going to have 1.399, whatever else. Let's go one more spot. 13996x plus 90.987. All right, so there you go. There is the best fit line, the least squares regression line for this set of data. All right, well, like I said, that's one way of doing this. There's actually another way you can do this, and I want to go ahead and show you this while we're here. If you go back into calc, or stat, I mean, instead of doing calc, let's go over to test. So there's all kinds of tests, as we know. But if you go down to the bottom of the list, you'll see there are some that say Lin Reg. These are linear regression tests. So you see there's Lin Reg T Test and Lin Reg T Int. By now, you probably know the difference, right? The Lin Reg T Test, that's going to be used when we want to actually test some sort of hypothesis with linear regression. And the other one is going to give us an interval. Also notice that it is a t-test. And remember, we use the t-test when we don't know the population standard deviation. And we have no clue what the population standard deviation. That's why I put t-test. All right, so I'm going to do this one, Lin Reg t-test. Hit enter. Again, it's going to ask me for my lists, L2 and L3. Frequency, just leave it as 1. And in terms of this, like B and P thing, if all you want is the equation, just leave it how it is. We'll talk about what this when we do the t-test. Then we'll if we're actually going to do a linear regression t-test for some sort of a hypothesis testing, we'll get back to what all this means. But if all we want is the equation, we just said it. So we've got our lists of data with frequency 1. When we do our calculate, and this time we get way more than just the slope and the intercept. I mean, we still have those. If you look on the kind of this bigger side over here, you can see the A, and you can see the B. And those are the same numbers that we found before. I wrote them down on the board. You can see that they're exactly the same. But this does give us a lot of other stuff. Like there is a t-score. Okay, well, yeah, there should be some sort of a test statistic. There's also a p-value. There's a degree of freedom. Like I said, we'll talk about what all that stuff is. And then you'll notice that there's an S, there's an arrow that says there's a little bit more. But it also gives us an S, this thing called R squared, and then this other guy called R. We'll talk about what those are in a little bit. Okay. But there's a bunch of other stuff that you get when you do it this way. So I actually suggest you do it this way. That when you want to find your linear regression equation, your best fit line, instead of just calculating it, do the test. Do the Lin Reg T test, because that other information is going to be useful for us later. All right, so that's how you can calculate it. Real quick, I want to go ahead and draw the graph of that line so you can see how it compares to the data points. So to draw the graph, I went to y equals. That was that first button underneath the screen there. And you notice it gives me all kinds of like y equals lines. I'm just going to type in the equation of my graph. So what I need for this one is 1.3996 x. Let me do it again. All right, my calculator froze up again. So here's what I'm going to do. Let's take a real quick break. I was going to take a break anyway. Let's come back in like 5 or 6 minutes. Go ahead and get up, stretch, get a soda or something. We'll come back in about 5 or 6 minutes. I'll get the computer so that it's actually letting me do the calculator stuff again, because I want to show you this best fit line against the data. All right. So I'm going to pause the recording and I'll be back in just a few minutes. You'll know that I'm ready when you see the screen again. All right. So I'll see you in just a few. Okay. So I got our technical difficulties figured out again, I think. So let's try this again. So I'm going to share the calculator view here. All right. So we're in the y equals. Remember where that came from? That was the y equals. So now we're going to punch in our equation. So I'm going to use the numbers that they gave us from the calculation. So we have 1.3996. And now I need an x. Well, to get the x, you're going to push this button right here. You can see it says x t theta n. That's basically your variable button. So if you click that, you notice that it gave us the x. So we got 1.3996 x. And then we're going to have plus 90.987. All right, so there's the equation for that line. And now I'm going to go to graph. And what we see here on this graph was our original data, but now also that best fit line. So if you look at this, you can say that, yeah, that actually does look pretty linear. The errors, the residuals are pretty small. I mean, for many of them, like look at this, 1, 2, 3, 4, 5 of those points. The line at least even touches the square from our points. And there aren't any that are really far away, right? So everything looks pretty good. So this is definitely a strong linear relationship. All right, so there's our best fit line. And through the magic of technology, we don't have to worry about those horrible formulas. It just gives it to us. All right, so that's how we can get it. Now, what about those other things that we saw in that list of stuff it gave us, right? There was a whole bunch more that it gave us other than just the slope and the intercept, but it gave us a bunch of other stuff. So let's talk about two of those things that are kind of important. The first being the R. So that guy R, you may remember that there was a number there that they give us that was called R. R is what's called the correlation coefficient. What it really is, what it really tells you is how close is your data to actually being linear. All right, so it's a measure I'm just going to call it this way, how close the data is to being linear. So that's what we use the R for. So here are some facts about the R. Some things to know about it that are kind of useful. I'll write them up over here. Okay. So first of all, R is always between plus or minus 1. So that R value is actually always between plus or minus 1. There's a formula for finding the R. It's even uglier than the one that's used in finding the least square regression line. So I'm not going to bother showing it to you because you are never going to calculate it. Your technology will always do it for you. Okay, but because of how we calculate it, it's always between plus and minus 1. All right, if R is equal to 0, this means that there is no linear correlation. You'll never see an R of 0. You might see some small R's, but you'll never see one that's 0 because this is sort of a theoretical. This would mean that any line that you try to fit to that data fails miserably. Well, because we're dealing with a finite number of points, you can always get something from it. But basically, the closer you get to 0, the worse this is in terms of linear. Okay, so basically, small r, bad. If we're talking about it being linear or not. All right, if r equals plus or minus 1, the data is exactly linear. Meaning all your data points are on a line, that best fit line goes through all of them, that there's 0 residual. Every point has a 0 residual. Okay, so that can happen, but it's also very rare. It's highly unlikely that when you go and you take data, even if it appears that there's a linear relationship, it's highly unlikely that everything ends up being exactly linear. there's usually at least a little bit of residual. Okay, but this is like best case scenario. So plus or minus 1, exactly linear. 0, no linearness whatsoever. And obviously, just like anything, we usually get the shades of gray. You get things that are in between. Okay, so you're going to see things like R is 0.87, R is 0.92, R is 0.16, right? You're going to get numbers like that, but it's always between plus or minus 1. Okay, so then what about the positive versus negative? Okay, well, if R is positive, that means that the slope of the line is positive. And the slope of the line being positive means that the linear graph looks like this. So that means that as we increase the independent variable, the dependent variable increases as well. Look at the example that we just did over here with the blood pressures. That one's going to have a positive R because that data was going up as we go to the right. As you get older, as you increase age, you're seeing an increase in blood pressure. If it were the other way around, that as you increase your independent variable, your dependent variable goes down, then R is going to be negative. All right, so that's really the only difference between positive and negative is what direction the data is going. Are we seeing an increase as the independent variable gets bigger, or are we seeing a decrease as the independent variable gets bigger? So when you're looking at it, if you get an R of negative 0.9, that should tell you it's just as strong a fit as if R was positive 0.9. It's just we're going down instead of going up. Okay, so that's it. All right, so that's what it means when we're positive versus negative. And so then the last thing I kind of want to mention about this in terms of the fact is like when we want to talk about a strong relationship versus a weak relationship, if that R value, if its absolute value is greater than 0.8, we're going to consider this a strong relationship. If that R value, or its absolute value, I should say, is less than 1/2, we're going to say that it's weak. If it's in between 0.5 and 0.8, it's sort of in between. It's not exactly strong. It's not exactly weak. It's just sort of there. We like the R values that are bigger than 0.8. You get an R value of 0.9 something, you're going to feel pretty good. You get an R value of like 0.6, you're like, an R value of like 0.3, well, that's garbage. That's not linear at all. Okay, so the correlation coefficient, that's probably, after the equation itself, that's probably the next most important thing to get from the calculator when it spits out all this stuff. Okay, because R is really a measure of two things. It's telling you whether we're going up or down, plus or minus, and it also tells you how good of a linear fit is. All right, so that's that guy R. When we did the calculation on the calculator with all that stuff, I don't know if I've still got it available anywhere handy. I do not. Well, let me just go ahead and do that. Let me share the screen again. And hopefully our calculator behaves. But we're going to go ahead and do that test again. So we'll do stat, arrow over to test, go down to the bottom of this page and do the Lin Reg T Test. it should all be set up for us because we haven't changed anything. All right, there it is. So let me arrow down so that we can actually see the R that's at the very bottom. But this one we've got R equals 0.97172. All right, let me stop sharing. So I went ahead and wrote that on the board. So we've got our R is 0.97172. So again, notice that it is between plus and minus 1. It is positive, which is telling us that our data is increasing. Okay, good. We saw that. Also notice it's really close to 1. 0.97 is not very far from 1. And so we're definitely in that strong relationship. All right. So we would say at this point that there is a strong correlation, strong linear correlation between age and blood pressure. So if we went into the study thinking that there should have been, oh yeah, you know what we think is going to happen is we look at people that are older, their blood pressure is going to increase. This sample would definitely suggest that is the case. All right, well, we still need to later talk about, null hypothesis and rejecting versus failing to reject and all that. We'll get there. All right, anyway, so R is one of those numbers that you get from the calculator. Now, there was another number in there that was R squared. And R squared's another kind of big guy. Let me actually go ahead and write down what it was for this set of data because I've still got it up on my computer. So I think we're going to want to look at it here in a minute. Let me grab that. It was 0.94424. All right, now it is exactly what you think it is. It's take this R and multiply it to itself. It gives you this guy, R squared. Well, that R squared, what it's called, write it up here, we don't need that anymore. R squared, this is the coefficient of determination. All right, so coefficient just means it's a number. But of determination, okay, so what the hell does that actually mean? All right, well, think about it this way. Think of R squared as a percent, right? And as a percentage, you can think of this as what percent changes in the independent variable, or what percent of changes in the dependent variable are due to changes in the independent variable. So written in words, it's a little tough to see, but let me kind of walk through this example. So think about this as a percentage. So 0.94424. Right? As a percent, this would be 94.4%. So this coefficient of determination, what it's saying is that 94.4% of the changes in the blood pressure number are due to the changing in the age. So there's a remaining little bit. Well, that's just telling us that there's not a direct linear relationship between age and blood pressure. If these had been exactly aligned, this R squared would have been 100%, because it's 100% match. Right. So the stronger R is, the bigger R squared is going to be, which should kind of make sense. All right, but that's why you'll get that number as well anytime you do that test. So you get your R and you'll get your R squared. All right, so these are the important numbers. The next thing is going to be, how do we interpret the data and use it to tell us what we want it to tell us. But I think I'm going to leave that for next time. I don't really kind of want to start getting into that topic just yet. And I could show you another example, but I think I don't trust my calculator. I'm having trouble with it, obviously. But I think you see what you need to do. You take your data, you put it in as lists, and then run that Lin Reg T test. And it will get you all your important information. So I think we're going to leave it here. What we'll do next time on Tuesday, we'll kind of wrap up our discussion on this by looking at doing hypothesis tests with linear regression and see how that relates back to what we were doing before. All right. So just a couple things to remind you. We're in the home stretch, guys. We're definitely in the home stretch. There's homework due tonight at midnight, the stuff from chapter 11. Tuesday, your projects number 2 are due. Make sure you get in and do that. I'm going to move the chapter 12 homeworks to being due next Thursday. Again, give some more time since we're kind of in the middle of that chapter. So look for that to change as well. All right. So that's all I have to share. So I think at this point, I'm going to go ahead and stop our recording and wish you guys all a very happy weekend.